Hello. In this section, section 10.4, we're going to talk about special cases of the Fourier series where we can break things down in terms of just cosines or just sines. And we've already seen why we would want to do that. When we solved the heat equation in section 10.2, we needed to express our initial condition, f of x, that we got when t was 0, as a sum of the eigenfunctions that we got from solving the equation. And so we needed our f of x to look like the sum of some coefficients times just sine terms, n pi x over L. And so in the problems that we solved, we were given an f of x that just was a finite sum of some sine functions, and we were really easily able to look up those coefficients. And in the last section, we learned how to approximate a function or represent a function as a sum of sine and cosine terms. But the question now is, how do we make a representation of f with only sines, or for that matter, only cosines? So the observation we're going to make is that we have our function f, which is defined from 0 to L. So let's say it looks like this. Okay, so this is our f of x. And in our heat equation problem, for example, we only care about from 0 to L. But when we defined our Fourier series, we defined it on functions from negative L to L. So if we want, we can sort of define anything we want over on this side and then take a Fourier series there. And so if we sort of extend our function f over here in a clever way, then the Fourier series we take on this extension might give us what we want. And so another observation that we have from the example I did in the last video is that when we had in the example that we did was the negative 1 and 1 function that looked like, this. And that was an odd function. So we observed in that example that odd functions, all of our cosine terms were 0. All the cosine coefficients went away. So odd functions only have sine terms in the Fourier series. And we can see that in example 4 in section whatever chapter we're on, 10.3. So that's one that we did in the last video. And then a similar observation is that even functions only have cosine terms in the Fourier series. And we didn't do this example, but you can go and look at it yourself, or maybe I'll do it in lecture on Zoom. But we can see this in, which one is it? Example 5 in section 10.3. So now let's take some f. So let us have f of x, which is piecewise continuous on the interval from 0 to L. And let's say that we want to have a a series representation of this that only has signs in it. So we're going to define the odd 2L periodic extension of f as, and so now we're going to call this f sub O for odd of x. And we'll define this as being equal to f of x for x between 0 and L, and then negative f of negative x for x between negative L and L, or and 0, and then f0 is 2L periodic. So in the example we had before, we had an f of x, and now our FO between 0 and L, we're going to define it the exact same way. And on the other side, we're just going to do an exact reflection of that. So we'll have sort of a point there, and a point there, and sort of a thing like that. And you can see that this thing is symmetric about the origin, right? We can flip it around and it's almost the same thing. It's close enough. Anyway, that's the idea. And then just for fun, we'll extend this to be periodic. So we'll just repeat the same thing over and over again, so that it is defined on the entire real line. So this green one is FO of x. So now let's think about what our Fourier series would be for FO. So now we'll compute the Fourier series of FO of x on negative L to L. So that's FO of x is associated with a0 over 2 plus the sum from n equals 1 to infinity of an cosine n pi x over L plus bn sine n pi x over L. And then what do the an and bn look like? So an is given by this formula, 1 over L, negative L to L, f of x cosine n pi x over L. So this is actually FO of x dx. And just like we saw in the last video, this is an odd function. This is an even function. And that means the product of them is odd. And so one way to think about this, think about why this might be the case. Imagine one of our prototypical examples of odd and even functions are power functions. So let's say we have x cubed and times x to the 4th. So this is odd and this is even, of course. And then their product, you have to add the coefficients. So this would be x to the 7th, which is odd. So that's how you can kind of remember this if you can't remember it another way. Whereas if we have, let's say, an even function and an even function, x squared times x to the 4th is x to the 6th. So we get odd, oh, sorry, that's not odd, that's even. Even times even is even. and x cubed times x to the 5th is x to the 8th, and we get odd times odd is even. So that's sort of the trick for remembering what happens there. Anyway, the point of this is that this whole integrand over here in our Fourier coefficient is an odd function, and we're integrating it from negative L to L, and so everything cancels out and this equals 0. So we don't have any cosine terms in our Fourier series for this odd function. So now let's think about our sine coefficients. Bn equals 1 over L, negative L to L, fo of x times sine n pi to pi x over L dx. And this integrand is odd times odd, and so the whole product is even. And so because it's symmetric about the y-axis, that means that this integral from negative L to L is equal to 2 over L of the integral from 0 to L. Because now if we have an even integrand, we only really care, the only information that we need is what's on the right-hand side of the y-axis. And then instead of writing FO, we can write f of x, just regular f, because from between 0 and L, FO is the same as f of x times sine n pi x over L dx. So that's going to motivate us to just use the 0 coefficient, and then namely this one, to define a new series representation for f. So we can define the Fourier sine series of f of x on just 0 to L to be, we will associate f of x with just the sum n equals 1 to infinity bn sine n pi x over L, where bn equals 2 over L, the same thing we had up there, integral from 0 to L, f of x sine n pi x over L dx. Now, because this is actually just a regular Fourier series of our odd extension, we have all the same properties that we had from the last section about convergence to f at points between 0 and L. So here it is. This is how we represent a function as a sum of sine functions. Now, what if, we haven't seen this need arise yet, but you can imagine where there might be problems where you would need to represent something as a cosine series instead. So let's just kind of go do basically the same thing again and define a cosine series. So for a cosine series, we're going to want an even function. So let's sort of stop, and we'll define the even 2L periodic extension of f of x. And we'll do that basically the same way. So we'll call this E. F E of x is going to be exactly the same as f between 0 and L. And we'll define it as f of negative x for 0. Oh, sorry. Do that wrong every single time. Between negative L and 0. So an example of this would be, we have the function we had before, and on the right side of the y-axis, we'll make it exactly the same as f, and then on the other side, we will just reflect it right over the y-axis, and then we'll also make it periodic. So we will basically repeat the same thing, you know, for the entire real line. All right, so this is fe of x, this green one. So now we'll compute the Fourier series of fe of x on negative L to L. So that would be fe of x associated with a over 2 plus sum n equals 1 to infinity an cosine n pi x over L plus bn sine n pi x over L. And we know what these coefficients are given as. These are the regular Fourier coefficients. So let's do the sine ones first because we expect those to be 0. So bn are given as 1 over L, the integral from negative L to L, f of x sine n pi x over L dx. And of course, this is, well, first of all, this should be fe, and fe is even, sine is odd, and so the product is odd. And an odd function integrated from negative L to L is 0, just like we expect. And then our an are similarly defined. So this really is the exact same thing we did for the sine series. So hopefully this is super boring to you. Negative L to L, fe of x, cosine n pi x over L dx. And again, we have an even function and another even function, and together that makes yet a third even function. And so now we can just think about the integral 1 over L 0 to L, and we actually have to multiply it by 2, so we will do that. 2 over L. Instead of fe, because now we only care about what's between 0 and L, that's exactly equal to f of x times cosine n pi x over L dx. So we have almost the same thing. So now, again, we will define the Fourier cosine series of f on 0 to L as a naught over 2 plus sum from n equals 1 to infinity a n, just the cosine terms, n pi x over L, where a n are defined as 2 over L, the integral from 0 to L, f of x, cosine n pi x over L dx. And that's for n equals 0, 1, 2, etc. So the only difference between these coefficients and the regular Fourier series coefficients are the limits of integration. It goes from 0 to L instead of negative L to L. And we have a 2 over here, which you can sort of think of as making up for the fact that you are cutting the region that you're integrating over in half. Now there is an example in the section of how you can use this, how you can actually compute the sine series and use it to find the solution to a heat flow problem, but I think I will save that for lecture, and of course you can read it on your own. So that is it for section 10.4, which thankfully is a lot shorter than section 10.3. So this one video for this section instead of 4 like the last one. All right, thanks.